Where's the camera these days? Oh,
Hello. Oh, yeah.
Where is it? Oh,
I handed you a mic that wasn't on, so that's on me.
all right. Which one's the long one?
That one.
All right. Hello, everyone. What? Hello, everyone. There we go. Who's ready for some astronomy on tap? All right. So welcome, everybody. It's great to see all of you here. How many of you are brand new to Astronomy on Tap? All right. Welcome. That's awesome. Great to see you all. So we're going to tell you a little bit about what this is, but for the most part, you can guess it. It's going to be astronomy while we drink beers on tap. So pretty straightforward concept. And I'm Tracy Becker. I'm one of the hosts, and we have
Sam Hart.
Michael Velez.
Aaron DeLeon. Adam Bach.
I'm Beck.
And we'll be your hosts for the evening. If you have any questions, come up and find us. In the meantime, we can switch slides. All right.
All right.
I'll hand this over to Michael.
Astronomy on Tap? It's a worldwide phenomenon in many cities, and we actually have to update this. There's some cities that have been removed and added, but it's all around the world. People gather to hear about astronomy. And our specific Astronomy on Tap is fun, interesting, interactive, and gives you a chance to win prizes. As we have here, we have trivia at the end of the night, and of course, all of our presenters give great talks, so we hope you enjoyed tonight. And check us out on our social media. We have Instagram, YouTube, Facebook, and Twitter, where we post updates about our events and other cool, interesting things as well.
All right. Your itinerary for tonight, we're going to start with Dr. Josh Kammer, where he will talk about turning red, the colorful polar terrain of Pluto's moon Charon. Then we'll have a break to get our refills. Then there will be Astronomy in the News, brought to you by UTSA's Astronomy Club. Normally that's Caleb, but as you could see, Caleb here is giving our final talk, so we'll have a guest speaker for Astronomy in the News. And speaking of Caleb, he will be giving a talk titled After Apollo, Rediscovering the Moon. Looking forward to that. Next slide, please. Afterward, there will be trivia, that's right. And we actually just have some participation trophies for trivia this time. So if you would like some cool solar eclipse glasses provided by Robert Reeves, thank you. We will be handing those out. And UTSA. They're a package deal, I suppose. All right, now next slide. All right. Our first speaker is Dr. Joshua Kammer. Is that how you pronounce it? Kammer, okay. Josh is a San Antonio native who got his undergraduate degree from Texas A&M University in 2010, then went on to receive his PhD in planetary science at the California Institute of Technology, or Caltech. He joined SWERI's Boulder division in 2014, working on New Horizons, going to Pluto, which is what he's talking about. And then he moved back to San Antonio in 2016 to work at Southwest Research on the Juno mission that went to Jupiter. So, I would like to present to you Dr. Josh Kammer in Turning Red, the colorful polar terrain. Okay, yeah. Whoa. Yeah. As is tradition with Astronomy on Tap, Josh here has a drinking word. So when Josh says this word,
Methane.
There you go. So look for methane. All right, thank you. Oh yes, last thing, please text questions to that phone number, because we will have a Q&A session after the talk. Thank you.
Perfect. All right, thanks very much for the introduction. It's good to see such a big crowd out here tonight. Unlike February 1st, when we were originally scheduled and the whole entire city got frozen, today is a nice balmy 90 degrees, so that's Texas for you. As they said, I'm a San Antonio native, grew up here and went to high school, Central Catholic. I don't know, probably no buttons in the audience. Hey, there's one. And then I went to Texas A&M, so I'm an Aggie. Did my degree in chemistry, so I have a background there. But what I'm going to talk to you about today is the really exciting science that the New Horizons mission brought back from the Pluto system. And Pluto itself is a really amazing planet. I did say planet. Charon being its biggest moon, I actually like to think of as a double planet system because the center of gravity of the two objects is actually outside of both of their surfaces. So Pluto and Charon being a really unique binary system surrounded by many other smaller moons made for a really fascinating topic of research in my career to start here at Southwest Research Institute. So it all does start with New Horizons, the mission that launched in 2006, 17 years ago now. I was still in high school, just graduated high school at the time, freshman in college. Makes me feel old to think about that, but it took quite a while to get from Earth all the way to Pluto, even though it had help along the way when it flew by Jupiter in 2007. And it got a gravity assist, and it shortened the amount of time it would take to get to the Pluto system by several years, thanks to that kick from flying past Jupiter. This is a common theme for a lot of our planet missions. If you can fly past Jupiter and get an extra kick from its gravity, you save a lot on fuel to get out to the places you're going. Well, then in 2015, coming up on 8 years ago now, that was the big flyby. That's when we saw for the first time from up close Pluto on the left and Charon over here on the right. They're, as you can see, roughly to scale in terms of their relative sizes. So this is one reason I think of them as a double planet system as well, is because Pluto's large. It's just under 1,200 kilometers in radius, but Charon's about 600 kilometers in radius itself. So it's pretty big too. They're both still fairly small compared to, say, our own moon, but being the biggest things out there in the Kuiper belt, they certainly qualify in my mind again as a true planetary system. New Horizons, the spacecraft, had a whole range of instruments on it to take pictures like the one I just showed, but also spectra and information about different wavelengths of light that told us a lot about what the surfaces were made of, what the atmosphere on Pluto was made of, and especially for what I'm going to talk about today, I've been looking at the visible light images from LORI, the LORI instrument, and then MVIC is part of the RALPH instrument, which has both visible and infrared light channels. So you pick filters for certain channels of light, and that gives you a spectrum between all those colors put together. So as I was saying, the spectrum that we're looking at when we look at the color of Charon's red spot up here can be seen in these 4 different channels. There's wavelength on the bottom in nanometers. And if you think of visible light, this tends to span this range, 300 to 700-ish. You have your blue end and you have your red end. MVIC also has these infrared channels to get at what the infrared is doing as well, reflected from the surface. And what we saw from the data when it came back from New Horizons is that this red pole is very distinct compared to the rest of the surface, which is more or less a gray color. And that red pole has been one of the major topics of study at Southwest Research Institute over the past 5 or 6 years since the data came back from the mission. And the way that we're understanding what formed the red pole was to think about transfer of material from Pluto over to Charon. So Pluto has a predominantly nitrogen gas atmosphere, just like our own, but the minor species in Pluto's atmosphere are methane. And that methane gets transferred over because it escapes the upper atmosphere of Pluto. And when it gets trapped onto Charon's surface, it bounces around a lot. If it's in the sun, there's enough energy to keep it moving until it finds a cold spot, which is often on the night side of Charon. The Pluto-Charon system is tilted such that the night pole has a really long time where it doesn't see the sun at all. And so that region can just freeze all of the methane gas that you ever get from Pluto. And so understanding what happens to that over time is something they came up with this right after the flyby. It gets accumulated at the pole during nighttime, and then this IPM Lyman alpha, this is the interplanetary medium Lyman alpha, this is a particular wavelength in the ultraviolet part of the spectrum that has enough energy to start breaking the bonds in the methane molecule. You like this slide, don't you? And so this happens during the nighttime, and that gets converted into these hydrocarbons that have something of this red color. But what we've been trying to work on is understanding that process from beginning to end, right? And so in the lab at Southwest Research Institute, we have the ability to deposit methane ice in layers at the same time as we're bombarding it with these Lyman alpha photons. And so we created this scheme under which we talk about phi, this Greek symbol here. It's just a ratio of how quickly we're adding more methane and how quickly we're adding more Lyman alpha photons in order to understand what combination, what ratio has an effect on the hydrocarbon products that are created. And so this is just a quick schematic of what this looks like in the lab. There's the input for the FUV here. We're measuring what we're seeing as well, the fiber optics. There's the FTIR to measure the infrared spectrum of the product. And everything in the middle here, this is where we're depositing that methane ice. So there's a whole range of instruments here from which we get a lot of great data to understand, again, what this process does at Charon under similar temperature conditions. And so this is just another quick spectrum, again, showing that difference between a high phi and low phi case. If you have a lot of that methane being deposited relative to your Lyman alpha, you get different products than you do if you don't have as much deposited at once. And primarily over here on the right side, you see for this high phi case, you get mostly ethane. This is just the C2H6. So ethane, not methane. Whereas in low phi cases, you get all these chained hydrocarbons, many of which are thought to form things called tholins, things that produce a reddened color. And so that's what we're trying to understand, again, that chemical process that's going on at Charon. So how do we understand it in the context of Charon's history? As I mentioned, temperature is a really important factor here. And so what we have is a thermal model for what the surface of Charon at the pole, what temperature it's at over its full seasonal cycle. The year in the Pluto system is several hundreds of years on Earth. So you can see here that New Horizons arrived here 2015. Shortly after the northern spring equinox. And so things in the north were warming up quickly at the pole, the solid black line here, from a low of below 20 Kelvin. This is extremely cold. Not as cold as, San Antonio in February 1st when it was freezing, but still pretty cold. And it warms up from below 20 all the way up to almost 60 Kelvin at the pole. And during this time, it's passing through the evaporation, sublimation temperature for methane ice. So that stuff that was previously frozen at the poles is now going to be sublimated away and start being transferred to the other side of Charon. And so this seasonal cycle is something that we've done exospheric modeling for to understand, okay, we have the laboratory measurements to figure out what has happening to the ice. Now we have an exospheric model that takes ice at the pole and over the seasons transports it to the other pole and back and forth while it gets processed each cycle into these higher order hydrocarbons. And so what we end up with is a distribution of these higher order hydrocarbons near the pole primarily, because that's where they're sticking around the longest. And so you can see from what this polar projected image of the reddened pole looks like that, there's a nice correlation there in this production of these products of methane. But wait, ethane itself is not red. So we figured out at the pole you have high phi, and so you are producing a lot of ethane as a product, but it's not red all by itself. So how do you get to the next step? How do you take that ethane, process it further into these other hydrocarbons that would produce a red color? Well, as I kind of pointed out on the plot here, if you're watching closely, during the night there's no solar wind, right? You're on the other side of Charon, you're not seeing the sun at all. But as soon as you come back out past the spring equinox, then you're in the solar wind again. You have a combination of solar and interplanetary medium Lyman alpha. And so the thinking is, before you get too warm that you're escaping off the pole and you're not sticking around long enough to undergo processing, the thinking is the solar wind can act as an additional processing agent to turn all that ethane into these higher order hydrocarbons that have a red color. So that's where we are currently with our research. We just got a new grant from NASA to work on this project, and I'm looking forward to having more results to share with you in the near future. Thank you.
All right, thank you, Josh. Reminder to everyone, please text your questions to the number. There's a lot of people tonight, so I'm only going to be doing it from the phone. We're not going to be raising hands or anything, so we'll get them in. And online, is there a way to modify the PowerPoint on the computer, Tracy, just for online? Methane. All right, that was one of them. So the first one, why isn't the polar spot circular?
That's a great question. Let me point you to, this picture will do it pretty well. One of the things you might notice about Charon is really dramatic topography. So it's not a perfect sphere by any means. It's spherical roughly, but you have these large cracks in its surface and lots of craters, of course, because it gets bombarded by material like elsewhere in the solar system. But especially around the pole, you see there's a large escarpment and ridge, and I'm not a geologist, so I probably use the wrong terminology for that kind of thing, but there is a lot of topography. And so when you think about moving methane around on the surface, you could easily form localized regions where it's more cold trapped than others. It's more shadowed for longer when the sun starts to rise above the horizon. So yeah, the reason it's not perfectly circular, it would definitely be related to how that topography interacts with the seasons on Charon.
Very cool. Thank you. Do you know where the name Charon came from, by any chance?
Alan Stern, the PI of New Horizons, would probably wag his finger at me that I should know this, but I don't remember exactly the naming history of Charon. And there are some people who like to pronounce it Charon instead of Charon. It seems to me mostly whatever your preference may be.
All right. Is it uncommon for one body to transfer stuff to another body? So is what is happening here, is that normal or not normal?
That's a good question too. It's fairly unique for this kind of dynamic, but in other planetary systems in our solar system, you often get material from moons, for instance, from Enceladus is a great example in the Saturn system. It's spewing out tons of water, ice, and other hydrocarbons into the overall Saturnian satellite system. And so transferring material between bodies happens pretty regularly, especially if you're a small body that doesn't have very strong gravity. A lot of stuff at the top of your atmosphere could easily escape, and that's exactly what happens here.
Very interesting. Thank you. There are no more questions, so last chance for you to text them in, or else we're gonna move on. Or we can. Okay, fine. We can go in the room if anybody wants to raise. Oh, wait. We'll how much methane is lost? to space in the transfer process?
That's a good question. I would point to my colleagues over here who do more of the exospheric modeling for an exact number, but I do know as a percentage of the total that's lost from Pluto, this is fairly, I think, small, because you can imagine from Pluto you lose it in all directions, but then Charon is kind of grabbing it as it's orbiting Pluto once every 6 days, if I remember that right. So yeah, there's still a lot of the methane that gets lost to space instead of to Charon. And even once it gets to Charon, it'll still escape from Charon as well. There's only a small percentage of it that gets processed into these other hydrocarbons instead. So it's a light enough molecule that it definitely wants to just bounce off the surface and get lost to space.
All right. Yes, we have a question in the room. You know what? Come up to the center right here, because that way. Yes, thank you.
Thank you very much. Can you go back one slide?
Sure.
Okay, from 1850 to just before 2000, there's no solar wind, or I don't understand the chart that you had there. And then there's solar wind from there on.
Yeah,
You lost me on that one.
so this is for the north only. So looking from the perspective of the North Pole, this region, this time period is when it's spending its time in permanent night for that part of the season. And it's not until the spring equinox that the sun rises over the horizon again and it actually sees the sun, and that starts to, bombard it with additional Lyman alpha from the sun. The sun emits in all sorts of wavelengths, including. Exactly, because this is essentially one full year in Pluto's system. It's centuries, so it's a long time.
If you're not a nighttime person, don't go to. Yeah. All right, just so I can say it one more time, is this the same type of methane that cows produce?
Yep, CH4. It's the good old natural gas. So it's everywhere in the universe and in our solar system, and it's definitely on Pluto and in Charon.
All right, thank you. Let's thank our speaker one more time.
Thank you.
We're going on break. Be sure to get your refills and food if you haven't already. Please order from the servers in here. Do not crowd the bar. They do not like that. We will get in trouble. Oh, dear God. I don't have to say that, no. But I do want to say that if any of you take any interesting photos tonight and you share it and you're a social media person, put that hashtag so I can find your photos, and maybe I'll share them on behalf of the team, and we can all promote our event together. So, oh, and yes, we have our merchandise table over here. We have keychains, pint glasses, T-shirts, and lots of other little tchotchkes like stickers and posters and stuff. So be sure to come look at that. And we will see you in 10 minutes. Whose laptop is that? That one? Yeah, mine.
break time over. I hope everybody got their refills. And I hope everybody's ready for some news. I'm going to keep on rolling. All right. All right, here we go. Who am I? I am nobody. No, I am Aaron DeLeon. I'm a graduate student over at Sweary, filling in for our main anchor, Caleb Gimar, since he's giving a talk later on the astronomy news. Just a reminder of the agenda tonight. Right after the astronomy news, we're going to have Caleb Gimar speaking, and brought to you by Astronomy Club at UTSA. Breaking news: independent astronomers discover gas cloud near Andromeda. So tonight I will be talking about this and also some updates on rockets and a fireball over Texas, if you haven't heard. So for the skies in March, this is a simulation from Stellarium of the sky. This is around March 15th, just to give everybody a good idea of what's coming up in March around 8:30 p.m. Jupiter's on its way out of the horizon. Venus is still a little above the horizon. Mars is well placed, but it's kind of small, so bright orange dot unless you zoom in a lot. But do not miss the Orion Nebula, one of the greatest treats in the night sky. It's going to be at prime position almost every night for the month of March, so don't miss that if you're out in the sky or if you're out at night. So last month I wanted to tell you all about this so you can all go and try and take a peek at it, but you know, as we know, city froze over, and so now I just get to tell you about it. So the comet that came by the last couple of months, if you didn't hear about it, was first discovered about a year ago, and it was called the Green Comet. Most of them are green, and the green comes from carbon that's on the comet. So some rocket updates. NASA's Orion spacecraft landed successfully, and Starship, actually, that video is supposed to play, but it's okay. It's just literally it's splashing down. But other than that, Starship had a successful static fire, 31 out of 33 engines. I believe one was turned off right before they started the test, and then one, I believe, failed. So, but apparently enough to get to orbit. So, a successful static fire. We have to have our ads. Woo! Splashdown. I told Google Slides to play that automatically, but I guess it doesn't listen. We have yet to figure out how to properly embed a video into a slideshow. No, not we. I mean just like technology in general. It just never works. Okay, and about a week ago, no, actually about 2 weeks ago now, a meteorite came over the Texas skies in South Texas, over McAllen. The meteor exploded about 21 miles above the ground. That's what created the sonic boom that a lot of people heard over down in South Texas. And it exploded with the force of about 8 tons of TNT, which is a good amount. A conventional explosive device, like one of the greatest conventional explosive devices, is about 11 tons, just to put into perspective. And about, I want to say it was 2 days later, they went out hunting for the meteorite that came and impacted the surface. And someone found this chunk that we see on the screen about 2 days later. So a nice hefty chunk. And that obviously is a piece that came from the main asteroid that had exploded in the sky. How big is that? The asteroid? Or how big is this rock? That a couple of inches. It's just, almost looks like a normal rock, unless you know what you're looking for. We trust the guy who took the picture. If you can see credits are Robert Ward. So if you have any complaints, take it up with Robert Ward. But as the headline alluded, an international team of independent astronomers discovered an arc of gas of doubly ionized oxygen near Andromeda. Now, its origin is unknown, its location is unknown. And what I mean by that is we don't necessarily know if it's actually interacting with Andromeda. It could be just in the frame. It could be in the field of view. We don't really know. It was surprising that it was discovered. It took, I think, over 130 hours or so, something like that, of total integration time for the images for this to be brought out, and also dozens of astronomers from around the world, independent astronomers, to capture this data. Woo! No, Astronomy News does not have a word because we want you to get it home safe. But yeah, so that was some of the updates. Of course, there's oodles and oodles of JWST data. It almost is becoming exhausting with how many updates they have. I wanted to squeeze one in, but there were so many I couldn't pick, to be honest. And my credentials will be stripped if I failed to forget to tell you about the upcoming solar eclipses. Mid-October, we have I want to get this right because I switched them up. I believe that's the annular eclipse in October. Yes. We have the annular eclipse coming up in October. The path, I believe North San Antonio was in the path. All of San Antonio was in the path. I switch these up all the time. And then next year, next April, we will have a total solar eclipse. And then that's the one, North San Antonio gets a cut of the path of totality. And on that note, as mentioned earlier, we have eclipse glasses donated from Robert Reeves and UTSA for everyone who sticks around for trivia. Those will come in handy to look at these. Do not, please don't look without proper PPE. And on that note, I will let Michael tell you about how to become an eclipse ambassador.
Yes, it's very exciting with both of these eclipses coming up. San Antonio is the X marks the spot. So we have a unique opportunity here to be ambassadors for these two eclipses. And everybody in this room is eligible because the program will welcome undergraduate students, or students in general. How dare they not mention grad students? Amateur astronomers, science enthusiasts, and scientists from all disciplines who want to engage their communities. And everybody in this room, you're a science enthusiast because you're here tonight. So you will receive virtual training, outreach materials, solar viewing glasses, so these glasses, assistance finding local outreach opportunities, and a supportive network of astronomy outreach experts. So basically, you will be an expert at this eclipse. You will know everything you need to know about the eclipse, and you can tell anybody, any of your friends, and any your coworkers, everybody about these two eclipses, amazing opportunities. And let's spread the word, and let's get people to San Antonio to watch both of them, October and April. Book it.
All right, so Caleb earned his bachelor's in 2015, his master's in 2019 from Wichita State University, and he is now a PhD student at the UTSA SWIRI Joint Program. Fun fact, Caleb was a space science educator at the Cosmosphere in Hutchinson, Kansas for 10 years. So without further ado, let's give it up for Caleb Gimar.
Thank you. I'll go ahead and wait for the slides to come up. There we go. Okay. All right. So, yes, my drinking word this evening is crater. There are many of those on the moon, as a point of fact. Indeed, a lot of craters up there. So, all right. Good. Already got the hang of it. All right. So, my talk begins with an ending. The Apollo 17 mission. Just a little over 50 years ago, if we would have done this when we were originally going to do this back in, at the end of January, beginning of February, it would have been just a month past 50 years ago or so. So it's a little farther, but nonetheless, about 50 years ago, the Apollo 17 crew traveled to the moon. This is indeed that crew. Eugene Cernan, commander, Harrison Schmitt, lunar module pilot, Ron Evans, command module pilot. Very special mission for a number of reasons. First of all, Harrison Schmitt there, the only scientist astronaut to go to the moon. And he actually is still around today. In fact, I had the great privilege of hearing him speak at an event at that space museum that was mentioned, the Cosmosphere, some time ago. So anyway, This mission collected around 110 kilograms, about 243 pounds of lunar material. That's most of any mission during the Apollo program. It spent about 75 hours on the lunar surface, the longest stay time of any of the Apollo missions. And not only that, it traveled about 19 miles across the lunar surface. The farthest distance traversed by any of the Apollo missions, of course, enabled by the use of the lunar roving vehicle. And it explored a region called the Taurus-Littrow Valley region. So that's just a little below the crater, yep, there we go, Littrow there on the moon, Taurus Valley region there. And it was chosen, this particular region, because it was a very geologically diverse region. They could pick up rocks both from, some highland regions nearby, and then, of course, there was a good amount, of course, the more what we call Mariae, or that's Latin for sea, some what we now know to be dried out isn't the best word, but certainly a dormant lava plain areas in the moon. Now here's the thing though. It wasn't supposed to end this way. It was not supposed to end this way at all. In fact, the original Apollo program plan called for a total of 10 lunar landing missions, of course starting with the first one, which landed at Mare Tranquillitatis. And then the next mission, Apollo 12, was supposed to go to the Ocean of Storms, and that actually did take place as planned. But eventually things got a little out of whack. It became only 6 lunar landing missions. And the reason why this happened was for a variety of factors. One was lost completely by accident. That was Apollo 13. The landing on that mission was aborted due to an in-flight emergency. So Apollo 14 was retasked with its landing site, the Fromoro Highlands. The Apollo 15 mission was actually rescheduled for a different reason. Get to that in a moment. The first of the latter missions to be canceled was Apollo 20, not because of budgetary concerns. That's something that's often said, not necessarily the case. It was actually a technical concern because of the Skylab program. They needed the Saturn V for the Skylab program. Their original plan of using a smaller rocket to loft Skylab did not work out, so they had to cancel 20 for that reason. And then the original Apollo 15 mission was canceled for budgetary reasons. They moved forward the mission manifest such that 15 would basically be one of the extended missions later planned. 19 was canceled, so that left only 15, 16, 17 as long-duration missions to the moon, where all of that really nice coverage of the lunar surface with the large sample return took place. Now, this led to quite a long time, particularly here in the United States, but even to some extent worldwide, of not having any missions to the moon. But it wasn't just for the moon. It was also for many of the other destinations in our solar system as well. Mars went from 1976 to 1992 without a major mission. Venus, 1978 to 1989. The gas giants, you had Voyager in the mid-70s. We didn't send another probe to the gas giants until 1989 with Galileo. And everybody kind of has their own ideas of why this all took place, why you had the kind of gap in exploration. There are monetary reasons, political reasons, but I think there's a very simple reason why. In order to capture everyone's attention, you have to go alien hunting. Yes, we didn't find the Romulans out there. We didn't find the Klingons. We didn't have these great space battles out there. We found what appeared to be mostly dead worlds for the most part. But there's really more to the story when you actually look into the details of what we did find out there. And that was especially true when we actually looked at the samples brought back by the Apollo missions. So in that time period, between not having a lot of these missions to the moon, it gave us a great opportunity to examine the rocks that were brought back from the lunar surface and some of the other data that was returned and be able to discover a lot about the moon. What we found was the moon was a much more fascinating world than what we could have ever imagined before. So all 382 kilograms worth of the moon's secrets, over 800 pounds of moon rocks, told us about this world that actually was a lot more geologically active in the very distant past than anyone thought. So I have a few photographs of the lunar rock samples here. The two up here from the Apollo 11 mission. The one that you see on the left there, that is a basalt. That rock is the kind of rock you'd expect to be indicative of early volcanism. And that was something that had not been expected before the Apollo missions landed on the moon. So this finding of these basalts actually was something of a surprise at the time. And what it indicated was that in the very distant past of the moon, there actually was a rather active surface with a lot of these outflows of magma that, of course, have since cooled off, leaving behind those basalts. And then you have a rock like this one. That's a breccia. And that is basically a rock that has been, how should I say this, extruded from an impact event. You have a lot of these meteors that hit the moon, produce a crater, and you have these rocks that are strewn out from that. And these breccias are actually rather important. They tell a lot about the past history of the moon, those impacts that took place, when those impacts took place, etc. And then you had some more specific rocks to the interior history of the moon. So these two lower rocks are from the Apollo 17 mission, and they are actually ones that have been determined to have been basically kicked up from the very deep surface of the moon, and those particular rocks give us insight into the interior structure of the moon. And the Apollo missions did reveal that the moon, far from being just this uniform body, actually is a body that has a crust layer, a mantle layer, probably a core layer, again, much more complex than what was originally envisioned. Now, if you do this kind of interesting thing where you plot the ages of the various rock and soil samples and correlate them with the craters in those, yeah, there we go, that number of craters in those regions, you find that the craters going back this direction, this very old time, are rather numerous. And then you have this time period that's a little less well understood, and that's probably one of the greater gaps in our understanding of the moon. But generally, though, thought to be rather flat in production rate. Then you get some of these very new regions. We have some rocks from the Apollo missions that have been determined to be from the Copernicus and Tycho crater impacts, and those in particular are thought to be a rather young impact regions. And what it appears is that this cratering rate very early, or at least fairly early in the history of the moon, was rather high. And some have interpreted this to mean that there was this period called late heavy bombardment in the very early history of our solar system. So you have this violent stuff taking place where all these large bodies are crashing into each other, and there's all this formation happening of the various planetary bodies in our solar system. Toward the end of this, you still have a lot of this cataclysmic bombardment. Now, there is some controversy about this, so this is not necessarily an open and shut case. But nonetheless, though, this distribution does imply something rather interesting about the early history of our solar system. And by the way, these rocks that were recovered from the lunar surface are some of the oldest unaltered rock samples that we have in our possession. Rocks that are nearly 4 billion years old, some exceeding 4 billion years old. The oldest one's about 4.5 billion years old, just a few tens of millions of years younger than the age of our solar system as a whole. Now, the funny thing about the rock samples was that they were pretty similar to Earth samples in the sense that the oxygen ratios in the rocks were about the same. Many of the minerals were about the same kind of minerals, but there was a lack of some iron-bearing chemicals. And that leads us to wonder, how did the moon form? Did it form from a cloud of material with the Earth at the same time? Probably not, because again, they are different enough in composition that something else interesting must have happened. But yet the moon couldn't have been captured from elsewhere, because the samples in their composition are pretty similar to the Earth all the way around. So the idea that has been proposed is that way back in the very early history of the Earth, a Mars-sized body called Theia impacted the Earth, and the kickoff from this impact produced our own moon. Most of the material that was Theia kind of went toward the moon, but some of the heavier stuff stayed toward the Earth. Now, this simulation here shows that impact event taking place. I actually wish I would have replayed, but if you want to see more of these videos, kind of take a look at that website there. That's a really cool website to go to. Go backward. It's a little bit of a long video, but yeah, there we go. All right, I'll let you watch it a little longer here, but I will have to go on because obviously short talk. Yep. But yeah. So this group that does these simulations, they're based at Durham University in the UK. They do a lot of these simulations of various large impact scenarios. Very, very fascinating stuff if you ever get the chance to read about it. So we'll go ahead and go on. So with all this new information about the moon that we gleaned from the Apollo samples, there was something of a buildup in interest of the moon, but it still really wasn't enough to justify an extremely expensive mission. So there was an opportunity that presented itself, and a rather odd one. There is an office in the Defense Department, many folks may remember this, called the Strategic Defense Initiative Program Office, the Star Wars program, as it was derisively called. And the engineers on this program had a rather interesting idea. They thought about putting like 1,300 satellites in orbit around the Earth. Each of these would have a missile on board. And on board each of these missiles would be a series of special imaging sensor devices that could pick up an ICBM launch in the Soviet Union, and then that missile would be directed right at that ICBM, and it'd blow up the missile before it would actually launch its warheads toward the United States. No one knows whether this will have actually worked or not. They never implemented it fully. I like to envision it as Starlink, except maybe as devised by an evil Bond villain of some kind. Nonetheless, though, the Strategic Defense Initiative Program Office kind of got NASA and the Naval Research Lab and all these things together and said, we want to test the sensing technology for this program. And what a better place to test it than the moon, an object that we know very, very well and can get really great data from. So they made this satellite. It actually has a long name, something along the lines of Space Technology Demonstration Platform, but they had a better name for it, Clementine. And the reason why they called it Clementine was that there's that old folk song, "Oh, my darling Clementine, you'll be lost and gone forever, Clementine." And the idea was that this satellite would be lost and gone forever at the end of its mission. It was going to go to the moon, orbit the moon, then go on to an asteroid called Geographos and get some data there. Now, it didn't wind up going on to the asteroid, but it did go to the moon, and it gave us a lot of really great information about the moon. It provided the first full mapping of the lunar surface, including these polar regions. It provided imagery of the moon in different wavelength bands. So like this image of Copernicus crater, right here. That image of Copernicus crater actually shows different ratios of the color bands. This is a mirror image showing differences in mafic mineral content. So this actually opened up our eyes to a lot of the surface chemical distribution on the moon. But the most fascinating finding from Clementine was a later finding from the mission. And that was Clementine actually beamed a series of radio waves at different frequencies to the polar regions of the moon. And then the reflections from those were detected by radio telescopes in the ground. And the spectrum of the radio waves detected indicated that there might be large quantities of water ice at the poles of the moon. And this got everyone's attention. Now, how could this be? Well, toward the poles of the moon, you have these craters, and the moon is very, very, very slightly tilted on its axis, so much so it's almost negligible. It's like 6 degrees. It's a very, very small tilt on its axis. And so the sunlight never reaches the bottom of these craters. And you have temperatures at the bottom of these craters that get down to somewhere in the neighborhood of around about 50 Kelvin, possibly even down to 25 Kelvin. Very, very cold, cold enough for water to deposit as ice toward the bottom of the craters. Now, the evidence from Clementine was not really enough for everyone. So guess what? We sent another probe. Lunar Prospector, 1998. And Lunar Prospector made a lot of very key discoveries about the moon, but one of the things it did was it carried a neutron spectrometer on board, And this neutron spectrometer detected a depletion of neutrons toward the pole regions of the moon. And that indicates there might be water there, because water, is H2O. There's 2 hydrogen atoms, 1 oxygen atom. Those hydrogen atoms, there's no neutrons in the nucleus of a normal hydrogen atom. So depletion of neutrons, you have a indication that there might be water ice there. Now, they did try to impact, the mission managers of this program did try to impact the lunar prospector into one of these regions toward the end of the mission to see if they could see the dust from the impact with ground-based instruments and try and measure water vapor. Didn't work out. They didn't really see much from that impact. But nonetheless, though, it did start a large wave of lunar missions. And so when you head into the new millennium, you have everyone trying to launch something toward the moon, because suddenly the moon becomes a very interesting place, not only because of the possibility of understanding more about the early history of our solar system, but because water toward the poles might actually be utilizable. So in the 10 years there between 2003 and 2013, there were about 10 missions sent there. It was a truly international effort. United States, Japan, India, European Union, China all sent missions during this time. And it was a very successful series of missions for most part. But I'm going to only select a few of them to talk about for a limit of time, and because there's only a few of them whose results are completely relevant to where I want to go with this lunar water stuff. So the first one was Chandrayaan-1. It was launched by the Indian Space Research Organization, 2008. Mission ended in 2009. And it carried aboard a NASA-led instrument, actually. This had the United States cooperation, called the Moon Mineralogy Mapper, M-cubed. Yep, M3, Moon Mineralogy Mapper, anyway. And this one actually could take a look at these permanently shadowed regions, these craters toward the poles of the moon, and look at them in the infrared spectrum and see the features that may be associated with water. The next 2 missions, launched on the exact same rocket at the same time, Lunar Reconnaissance Orbiter and LaCrosse. And LaCrosse is kind of what's more epic to talk about, because it actually impacted the moon, or at least the booster impacted the moon. The spacecraft itself observed the ejecta from the booster impact, then the spacecraft itself impacted the moon. And it impacted at Cabeus Crater. There, yeah, all right. Yep, okay. So, yep, there at Cabeus Crater. And the Lunar Reconnaissance Orbiter itself carried on board an instrument, or carries on board, it's actually still operating, an instrument called LAMP, Lyman Alpha Mapping Project. And this instrument actually is a SWORI-led instrument. How many LAMP people do we have in here? I know we have a few. Come on. LAMP folks. Yeah, there we go. Okay, yep. All right. So this particular instrument observes the moon in the ultraviolet bandpass. And the cool thing about the ultraviolet bandpass is that you have all these background stars that shine very brightly in the ultraviolet, and even though the sunlight cannot reach these permanently shadowed regions, the permanently shadowed craters, the ultraviolet light from the background stars can, and we can actually observe what's inside of those craters in the ultraviolet light. So, and this is a little more complicated in terms of a lot of the terminology and why I really wanted to use this evening, but I'm using it for illustrating a very important point. And as each of these missions, the data from the missions implied a certain amount of water ice toward these polar regions, but over a wide range. So if you go to the M-cube data, it's looking for these 2.8 and 3.0 micrometer absorption bands. That's in the infrared. That was just simply an indication that these hydrated species, maybe not necessarily water, maybe even hydroxide, could have been there. You go to the LAMP data, and you get these observations called the 165 nanometer absorption edge. So just imagine you're seeing the part of the rainbow past the violet end of the rainbow, and suddenly toward the ultraviolet, the brightness just dips down tremendously. That's the absorption edge of 165, and that's indicative of hydrated species, possibly water ice. And depending on how you interpret the data, you could have 0.1 to 2% if mixed, 10% if exposed frost. There's even some indications that even on the day side, varying during the day, you have about less than 1% of a monolayer. I'm just going to say that's a really tiny amount. That's only a few parts per billion, if I'm not mistaken, right? Is that right? Parts per billion? I can't remember the actual number there. Right? Parts, okay, good, yep. Anyway, a few parts per billion there. Yeah, yeah, very, very tiny amount of water there. Anyway, so yeah, very wide range. And in La Crosse itself, I've detected about 5.6% water content per mass. The bottom line is this is not very well constrained, and especially when we're trying to look in that ultraviolet band. And what we really need is laboratory data on the reflectance of lunar surface soils in the ultraviolet, and especially hydrated species. And so here's the solution, and this is where kind of my part of the story comes in. I work with this thing. It's called SWRC, Southwest Ultraviolet Reflectance Chamber. And our aim with this experiment is to place actual lunar soils in the chamber, hydrate them with a little bit of water vapor, cool the sample down to the temperatures like we find in these permanently shadowed regions, you know, that a few tens of kelvins temperature there, and then measure the reflectance of the samples and see how that absorption band at 165 nanometers changes, and maybe be able to correlate that with a certain amount of ice, and then we can get a better fix on what we're reading back from a lamp at the moon. So within the chamber, you have this sample tray here. That sample tray is where we put the soil samples. There's a detector here. It's what we call a channeltron detector. That's basically a fancy term for a detector that's very sensitive in the ultraviolet bandwidth that we're interested in. They can observe the reflected light. On the outside of the chamber, there's this deuterium lamp that exposes the sample to ultraviolet wavelengths. And the light reflects away from the sample, and that can be measured as such. And we can get an idea of how well it reflects in different angles. This armature is movable there. So basically, allowing us to replicate what LAMP does, at least measuring this reflected light in a laboratory environment. Now, we have published a couple of studies. Actually, I published one. My advisor, Ujwal, he's sitting right there. Come on, raise your hand. Yeah, there you go. All right, yep. Ujwal's published one of them. And the one study that Ujwal published et al., and of course many of us, some of us are here in the room, they're on that group at least, was on the reflectance of an actual Apollo soil sample, the Apollo 11 soil sample, one from Mare Tranquillitatis. And then my paper covers the reflectance of simulants, things that are Earth-based soils that are very similar to what we find on the lunar surface in terms of their general mineralogical composition, etc. So this is the way these samples look. That's the Apollo 10084. We use a very small quantity because we don't have an awful lot of this to use. It's just a very slight amount. But nonetheless, that is actual soil returned by the Apollo astronauts. Actually, Neil Armstrong, Buzz Aldrin collected that back in 1969. We have used this in the chamber. We've measured its reflectance properties in the chamber. And then you have JSC-1A and LMS-1. Those are the two simulants, the two Earth soils. They're very similar lunar soil. And what we found in comparing these reflectances is rather interesting. We found one that the Apollo 10084 is very dark in its reflectance generally, but the simulants are a little brighter. And the LMS-1 simulant's a little closer to the Apollo, so but again, still generally brighter. The brightness of these samples altogether increases toward a shorter wavelength end, so as you go more blue and light, the reflectance goes up. But that's especially dramatic for JSC-1A. And putting all of this together, what we figured out is that probably the titanium content in the soil plays a role in this. The greater the titanium content, the lower that reflectance starts to get toward that shorter wavelength end. And then the soils reflect a little differently. Your JSC-1A and LMS-1, those two simulants, they actually are a little more forward scattering. They tend to reflect the ultraviolet light away from the source, impinging on the sample. And then the 10084 tends to be a little more back scattering. It tends to reflect light back toward the observer. So that, because the commonality is that the two simulants aren't space weathered, they haven't been bombarded by solar wind radiation micrometeoroids, and yet 10084, the 11 sol, has. That property may be indicative of space weathering playing a role. So where do we want to go after this? Well, we actually want to dose these soils with water, cool them down to temperature, and see how the reflectance changes. And we're on our way to doing that as we speak. And maybe from those experiments, we can get a little better idea of how much water ice there may be toward those polar regions. So I'm going to leave off with a dream, because that's really why this thing of water on the moon is so important. The idea is that maybe this ice toward the poles can be usable for lunar bases, human lunar bases, which can be a further springboard for doing other science in space. It can be a springboard for launching missions onto the more distant planets. Or they can supply these lunar bases where we can base large telescopes. And that's actually kind of a very intriguing idea to me. This concept illustration shows that, a large radio telescope assembly on the far side of the moon, where you're away from all the radio noise of the Earth, and you can get a really great view of the sky and radio wavelengths, maybe even find signals from an extraterrestrial intelligence. So maybe after all, the moon can help us with alien hunting as a point of fact. But nonetheless, though, it's about what the future holds, and I'm very happy to be a part of it, and I hope we find some interesting things from these experiments going on. And with that, I'll take any questions. Thank you. Thank you.
Thank you, Caleb. Thank you. And everyone, reminder, the number's on the screen to text your questions to. I have a number of them, so we will get started. I like this question. Is the amount of water constant, or does it fluctuate from what you see so far? Is there enough temporal data?
There's not really enough data
Okay.
to know that. And again, that kind of goes back to getting a good fix on how much is there. We really do not know exactly how much is there. Again, when you're varying from as high as 10% to as low as 0.1%, it's a little hard to get a good fix on that. I mean, I think it'd be sensible to assume that through time, it probably does vary some, because through time what's going to happen is, depending on the source of water, if the water is sourced from cometary impacts coming in and depositing the water there, or if it's sourced from some kind of an odd or combination, I should say, of solar wind protons and some oxygen compounds that eke from the soil, there might be an increase over time, but certainly we haven't observed anything like that yet, at least not to my knowledge.
Okay.
Yeah.
Thank you. Another question is, are you aware of what sort of science the Artemis mission is going to try to achieve at the poles, especially near the craters? Are you aware of plans, or is it still in the proposal stage? Are people still proposing?
I don't know. That's really a good question. I'll have to do a little reading up on that. It would certainly be interesting to see what kind of science is possible. Obviously, it's probably still somewhat in the proposal and fleshing out stages. There might be some folks in the room that have a role in the Artemis 3 science proposals and everything. But it'll be interesting to see what they do, and it'll be interesting to see what capability they have given, the readiness of the human landing system, et cetera. But, yeah.
Oh, yeah.
What is Artemis 3? Okay, so Artemis 3 is going to be the first human return to the moon since the Apollo program. All right, so we all probably have heard of Artemis 1. That was that test flight with the Orion spacecraft going around the moon back in November on into December, and then returning to Earth. Artemis 2 will basically be a piloted repeat of that mission. They'll go around the moon, come back, and then Artemis 3 will actually involve humans landing on the surface. So the crew will launch on an SLS rocket like what was launched back in November. They will meet up with the human landing system. As of right now, that's planned on being provided by SpaceX. They've modified their Starship concept for use as a human landing system. They will rendezvous with Starship at some point in time during the mission, and they will land on the surface toward the lunar South Pole, while these craters, and of course work on various scientific experiments there, and certainly be kind of a preparation for further exploration and utilization of those regions and resources. Yep.
Thank you. Very cool stuff. How do we know that the basalt rocks are from the moon being volcanic and not necessarily from Earth volcanism that was carried from that
G. Who is the goddess of the moon? Is it A, Artemis, B, Selene, C, Luna, D, Iris, or E, Gaia? Again, who is the Greek goddess of the moon?
You got it? All right, is everybody good with this one? Can move on? All right. Question 3, history. What is the name of the lunar mare where Apollo 11 famously landed? Caleb said this, so this is a memory recall. Woo! Is it A, Sea of Tranquility, B, Sea of Knowledge, C, Sea of the Edge, D, Ocean of Storms, or E, the Eastern Sea? Everybody good?
Going once,
All right.
going twice. Question 4. There have been 5,297 confirmed exoplanet discoveries. How many confirmed exomoon discoveries have there been?
Oh, no.
And that's trivia, folks.
There's no winners tonight.
Tracy got the bill and it said, "You know what? I think I gotta leave."
Computer checked out.
I'll tell you what. I remember the question. It was how many exomoons have been discovered over exoplanets. Oh, no, no. We're back. Presentation mode, but it will do.
Oh, well.
The only choice is A22. Okay, there we go. We're back. We're back. Okay, how many exomoons have been discovered? A, 22, B, 110, C, 2,036, or D, 5,223, or E, there are no confirmed exomoons.
Well, while you all think about this one, you know, I was thinking during Caleb's presentation that we really should get him to do our break time music after his beautiful rendition of Clementine.
There's a better version of Clementine. You want me to sing it after? I'll sing it after. And it would be fun. I'll sing it after. Maybe not well.
All right, going once, going twice. Next question.
All right, question 5. The lonely planets. Which of these following planets have no moons? Your options are Mercury, Venus, and Mars. So that's 1, 2, 3. And then the answer choices are A, 1, so only Mercury, B, 1 and 2, Mercury and Venus, C, 2 and 3, Venus and Mars, or D, all of them. So which of the combos?
No moons.
Yes, we'll answer the letter. Oh, you know, I forgot. Yeah. Everybody on your answer sheets, if you're putting letters, you're doing it right. If you're writing anything but the letters, you're doing it wrong. I'm just going to say it.
Objectively. We did not specify, so that's on us, but you know what? It's still wrong.
I can go backwards, but
we're gonna go through them one more time, just so everyone's got
Yeah.
the questions. All right, everybody got it? Going once?
wait.
We got someone back there.
We're going to give you a moon.
All right. Question 6. What year did the International Astronomical Union demote Pluto from planet to dwarf planet?
Boo.
Thanks, NDT. I'm only assuming that's Neil deGrasse Tyson.
Yeah.
All right.
We have
Is
his
it
book
A,
here.
1998, B, 2001, C, 2006, D, 2009 because it was laid off after the job market crash, or E, 2012? Budget cut, you know. If anything, that'd be antithetical to budget cuts. You gotta reprint the textbooks.
It's actually Mike Browning calls himself Pluto.
The Pluto killer. Everybody good? All right, that's it for the regular questions. But as always, we have a bonus. Today's bonus is list the following celestial bodies in order of smallest to largest. So they are Himalaya, Charon, Pluto, our very own moon, and the Earth.
Again, please, letters only.
They were all mentioned today, by the way, in some way, shape, or form. I know this one's going to take some time, so I'll leave it up for everyone, and then we'll recap questions 1 through 6 very quickly, and then we'll collect your sheets. So. How's everybody doing on the bonus? Anybody need more time? Yes? No?
Anybody need a question repeated? Speak now or forever hold your peace. All right, I guess everybody got it. Okay, we're going to come and pick up the scorecards. If you can hold them up for us, please. We would also please ask for the markers and pens back as well. We need those for the next round next month.
And we'll tally up the results, give the answers, and announce the winners. So.
In. All right, cool.
Well, we got to do the answers first. So.
Wait, you don't want to pick one first? See who wins? Call them up, ask them the question, see who wins, and then go through the answers?
I guess. All right. We're gonna do the answers in a little bit, but first we have a weird scenario. As many of you know, often when we have ties, we give prizes to both teams. But this is a 4-way tie. I'm not doing that.
So we need the following teams to please come up.
One representative.
We're gonna ask you one question because we gotta break the tie.
So I need one person from Team Derek, one person from Team X, one person from Team Jasmine, and one person from Team Heard About Pluto. So
please, one representative from each of those groups, please come up. We want to ask you one more question. Okay, now that we got that sorted out, we're going to go through the answers. Oh, wait. Michael's got to pay the check. Give us a second. Anybody got the Jeopardy song queued up? There we go. I hear it. There we go. Looks like Michael's paid. I feel like I'm entering my sports commentator era right now.
Where's my remote?
Oh, right here.
Oh, thank you. All right, everybody. All right. Question 1, which was about the Star Wars character that said, "That's no moon, that's a space station." It was Genital Kenobi. Obi-Wan Kenobi.
Hello there. All right.
Question 2.
The answer to question 2.
The goddess of the moon.
Who is the goddess of the moon? It is Selene.
A handful got that right. So if you got it right, applause to you.
I'm right there with you if you got it wrong. I honestly did not know the answer to that one.
The third question was about the amount of confirmed exomoons. And believe it or not, think about it, they're tiny. There are none. Zero. Zilch.
No, actually, that was
Oh.
we skipped one. Oh wait, hold on.
I
We'll get
skipped
back
one.
to that. We'll get back to that. The answer to the question 3 was the Sea of Tranquility.
I got ahead of myself. I'm sorry.
We got a little ahead of ourselves there. Forgive us. And the next question.
There we go, there we go.
There we go. There are no confirmed exomoons. So, yes, 0 confirmed exomoons. And as Michael said, they're tiny. It's hard to
They're really-
confirm an exomoon.
Really small.
Question 5. I don't remember the question. That's, yes.
The lonely planets.
Which of the planets have a moon? The answer is Mercury and... Oh, I'm sorry. Which of the planets have no moons?
No moons.
Mercury and Venus. I was confusing myself for a second. Mercury
Mars-
and Venus do not have moons.
Yes. Mars, of course, has Phobos and Deimos, which if you ever played Doom, you should know all about them.
They're little tiny moons, but they're moons nonetheless. Wait, hold on. I want to get the answer for number 6.
All right. Question 6 was about...
Was about something to do with Pluto. Oh, when was Pluto abolished as a planet and demoted to dwarf planet? The answer is 2006. Okay, I want to give everybody some context to this. So, when Pluto was demoted as a planet in 2006, that was also the year New Horizons launched. So, we sent a mission to Pluto to explore Pluto, and then that same year they said, you know what, Pluto's not a planet anymore. And I think that is incredible scientific drama. I love that story. I don't know how dramatic it was, but to me, I hope they were throwing fists. Some old scuffle.
It launched as a planetary mission. It continued as a dwarf planetary mission. All right, and then of course, last but not least, the bonus. The bonus, how could we do this to you? The answers were sequentially A, B, C, D, and E.
Did anybody catch the Himalaya? Did anybody catch the Did You Know during the first break? And now the secret's been revealed,
Somebody's
so
paying
stay tuned. There was a Did You Know during the first break, and it was talking about the size of Himalaya.
The first time we've ever done a Did You Know during the break, it showed up in a trivia question. Might happen again, just saying.
Now you know the secret. You got to save for trivia next time.
To all you regulars out there. All right, that was the last question, which means we have to announce prizes. So our four-way tie was broken by asking about the launch of New Horizons. Only one team was able to, multiple teams were able to get it right, but one team is going to win the prize of third place, and that team is, have you heard about Pluto? Come on, up for
Come claim your prize.
third place. Tonight, the third place prize is this poster right here, as well as stickers for NASA, and the LRO lamp instrument discussed today by Caleb, and a card set for the solar system. So interesting stuff. Yes, thank you. Round of applause. Second. Our second place tonight, which will win the aforementioned poster, NASA sticker, cards, and a New Horizons sticker, and then a special Celestron mug. Thank you, Robert. The Power Rangers. Yeah, come on, everybody. 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 No, oh, come on, everybody. Let's. No, wait. Do you want to do a photo? Photo? Yeah. Everybody, we do a photo op. All right, the moment that we've all been waiting for, the first place team of the night that will get that poster, NASA sticker, New Horizons sticker, deck of cards, and a Neil deGrasse Tyson book titled Astrophysics for People in a Hurry. So if you're in a hurry, read this book. Alan Stern Pluto. You just won first. Hello? Who's Alan Stern Pluto?
Did they answer and walk out?
Did they leave? This may be a AOT first. All right, the first prize has been vacated. Yeah, you've got to earn the prizes. So, we're just.
Alan Stern. No, it can't be usual. He didn't compete.
No.
Someone says Alan Stern Pluto here, that team name. Come on, anyone hear from it? No? You gotta be kidding me. All right. Okay.
Yeah, the poster will, we'll give, okay, all right.
Yeah, literally 3 people.
All right, well, okay, put the book aside. We'll save the book, but we'll get posters and we'll get the posters and some stickers for teams X and Jasmine, so, and yes, and you guys get the enthusiasm award of the night. Woo! All right. Yes. Thank you all. I can't believe that they left. Right? Like, who does that? No, exactly. Oh my. We'll make sure everybody gets compensated tonight. But thank you all for coming. I'm sorry that we couldn't see you all last month, but we're back, and we're going to be back again next month, April 5th, first Wednesday of the month as usual. Be sure, if you want more information besides our social media, you can scan the QR code and sign up for our email list. And, of course, a special thanks to our servers. Make sure you tip them generously if you haven't already. And the Blue Star Brewing Company for hosting us, and the Southwest Research Institute for their continued support for our event. So thank you, everyone. Everyone get home safely, please. And don't leave for trivia if you participate.